potential is a functional of the density. So in order to calculate how it varies upon a perturbation, you have to calculate the functional derivative of the exchange correlation potential with respect to the density. And this functional derivative will depend on two arguments, right? Because the exchange correlation potential depends on one argument by itself. But then I take the functional derivative of something that depends on one argument, but functional differentiation would add one more argument. So it would be a function of two arguments that is called the exchange correlation kernel, and you multiply by n prime. So this is an integral over r prime of the exchange correlation kernel of r and r prime times n prime of r prime. I should have written this, sorry for not doing this. And then we linearize the Schrödinger equation. But we learned how to linearize the Schrödinger equation, right? You have to do first order perturbation theory. That implies all these sums over empty states. We don't want to do sums over empty states. We want to avoid the calculation of empty states, and we know how to do. We solve this linear system. Basically, the solution of linear response functions parallels the solution of Kohn-Sham equations with the solution of an eigenvalue problem replaced by the solution of a linear system. Then the calculation of the response density is trivial. You have just to linearize this quadratic form, and this is very simple, like this. You have three steps that parallel one by one the three steps of the self-consistent loop of ground state density functional theory. You iterate them and you are done. The same way as this self-consistent cycle could be expressed in terms of a global minimization of some functional of the Kohn-Sham orbitals, exactly the same way this self-consistent loop can be expressed in terms of the global minimization of a quadratic functional expressed in terms of phi prime. I will not explain this, but basically what you have to do is, instead of deriving the Kohn-Sham equation and then linearizing them, you express first the Kohn-Sham functional to quadratic order in the orbitals, and you minimize that quadratic form, and you get essentially the same results. What about? I'll propose the following. Unfortunately, I have a very important telephone call to make in 10 minutes or a quarter of an hour. So I would ask you the favor and ask Andrea the favor to let me stop at 10:20, 10:25 at most. We make a break 10 minutes in advance. We start 20 minutes in advance. And I will take the first 10 minutes after the coffee break to finish my talk. Okay? Thank you for this. Macroscopic electric fields are black beasts, or have been black beasts of electronic structure theory up to 15 years ago. The reason is again formal, but deep in many sense. Suppose you have an infinite system and you apply an electric field to it. Nothing very strange, right? That you want just to measure the dielectric constant of a piece of an insulator. You have block states that are periodic functions times this plane wave term, and you add if you do perturbation theory, you see that the perturbation theory is done, we have seen, by multiplying. An essential ingredient of perturbation theory is the product of the perturbation times unperturbed wave functions. Right? The perturbation that describes an electric field is the X operator. So the operator whose gradient is a constant, the electric field, is X minus E times X. If you multiply an unperturbed wave function with such an operator, we'll end up with a wave function that is not of the block form. We are in a very bad shape, because in order to do perturbation theory, it is essential mathematically that the perturbation brings a function of the Hilbert space that describes your system onto a function of the same Hilbert space. But here this is not the case. You take a block function, you multiply it by X, and you exit from the Hilbert space that is supposed to describe the system. This is a very bad problem that has been solved by Raffaele Resta and David Vanderbilt in the mid-90s with what is now called the modern theory of electric polarization. I don't know if any of us will say something about this. I will not. But I will just, for the sake of perturbation theory, I will describe the fix that had been found before the modern theory of polarization, and that works perfectly for perturbation theory. It is just a fix. It is a mathematical trick. Don't ask me the physical meaning of this, because I don't know any. It has been demonstrated afterwards, though, that the modern theory of polarization, which has a firm physical ground, gives the same formula that had been used before with this tricky fix. Let me describe the tricky fix. So what you need to do perturbation theory, remember, is the projection over the virtual orbitals, the space of virtual orbitals. Okay. The space, I'm sorry, I was, sorry. The space of virtual orbitals of the product of the perturbation times the unperturbed wave function. So basically, what you really need in order to do perturbation theory is not quite the calculation of the perturbation times the unperturbed state, but you need something less. You only need the off-diagonal matrix elements of the perturbation between eigenstates of the Hamiltonian. Only off-diagonal. You see, there is no diagonal orbital. Here you have only valence states, and here you have only conduction states. It turns out that these off-diagonal matrix elements are well defined, even though the x times phi naught by itself is not. The reason is simple, and the reason is that you can express any off-diagonal matrix element as the matrix element of the commutator divided by the difference of the energies. Very simple. But the commutator between x and h is a periodic function. Hence it brings a block state onto a block state. That it is a block function, it can be easily seen, because the commutator of h and x is the derivative of x, is the velocity. And the velocity is the momentum. And the momentum is periodic. Right? Actually, it is a little bit more complicated than the momentum, because in actual plane wave pseudopotential applications, you also have the commutator between the Hamiltonian and the non-local potential. But for the same reason why the commutator of x with the kinetic energy is periodic, and it is the momentum, for the same mathematical reason, the commutator between x and the non-local potential is also periodic. and this off-diagonal matrix element of the commutator of the Hamiltonian can always be calculated. And but it seems that they can always be calculated, but it seems that in order to calculate this, you need the infamous empty states that you don't want to calculate, right? But again, you can play tricks. You define this function, that is, you take this expression for the right-hand side of the linear system, you plug in the commutator, and you end up with this expression that you call psi prime, and that you want to calculate without summing over empty states. How do you do? Again, you play the trick of the linear system, and you write down essentially a different linear system that gives you the right-hand side of density functional perturbation theory in the case of a macroscopic electric field. So you first solve this for an applied electric field. The solution of these linear systems would give you the right-hand sides of density functional perturbation theory. With those right-hand sides, you calculate, you start the self-consistent procedure that I have described before. So I would ask you to stop here at this time. We take a coffee break till 10:40, and we resume in 20 minutes. Thank you very much.